All right, hello everyone. Welcome back. We've got lecture video number 2 here for chapter 7, and it's all gonna mostly be on this concept here called steps for balancing equations. Right? It's an idea called balancing equations. Now it's not something we're gonna really focus on a lot of in the video, but we're gonna spend a lot of our class time when I see you next focusing on doing examples of balancing equations. So all I'm gonna really do today in this video is just kind of go over the steps and then kind of go from there, right? So when I saw you guys last, we spent a lot of time looking at stuff like this, right? How to count atoms of individual, formulas, right? So when I looked at and had you guys look at an example like this, for example, for 4Ca3PO4, right? Our main goal for this particular example here was to be able to confirm how many atoms we have of every single one of these pieces here, right? How many calciums we have? 12. How many phosphorus atoms we have? 8. And then how many oxygen atoms we have here? 32 overall, right? And being able to make that determination anytime you come across a formula that has either a coefficient, a subscript, and parentheses, or all of them, right? Anywhere in between. Right? Because being able to do this every single time is going to pay dividends when it comes to balancing equations. So let's go through each of these 6 steps here, and then we're going to move on. Okay, so number 1, write the skeletal equation with all formulas, and we're going to spend some time going back to that stuff that we did not cover in class the other day, which is these skeletal equations, right? But basically all they are basically naming off in doing that English language to chemistry translation, right? Translating, if necessary, from any English language words into our language of chemistry, right? All you need to be seeing right now when it comes to balancing equations are chemical formulas, right? We don't want to see any English language words, just chemical formulas that come from our reference table, right? All of our atomic symbols are NaCl versus sodium chloride, right? That's step number 1. Step 2, count the number of atoms on each side. Right, when I say each side, we have to use that arrow to differentiate our reactants on the one side versus our products on the other, okay? Number 3, change the coefficients to balance, right? So we learned very recently what a coefficient is, right? It's the number out in front, right? So if I look at NaCl, for example, right? I look at this formula here, there are no there are no subscripts here. There's technically an invisible subscript of 1 and an invisible subscript of 1 in front of our Na and our Cl, right? But as soon as I put a coefficient of 2 out in front of here, right, that changes the number of Nas I have, right? What I'm trying to say is this. In step number 3 here, guys, you are able to change the coefficient to balance each of our sides of our chemical equation here, right? So this number here out in front, this coefficient, can be changed and altered depending on what formula you're looking at and how many atoms of the individual pieces of that formula, right? So that is step number 4, or number 3. So number 4 is to recount the atoms, right? So you're essentially going to repeat this process then into step 5 until the amount of each atom on the right is equal to the amount of each atom on the left. So you basically are going to, step by step by step, change coefficients in the chemical formulas of our equation, and then recount the atoms to see if that's balanced our total number of atoms on either side. And you're going to repeat that until you have a complete balancing of all of our atoms on both sides of our equation. And then lastly, we're going to ensure that the simplest ratio of coefficients is used. That should be a no-brainer. Right, simplifying ratios is a pretty common practice in chemistry. Really, the only time we haven't seen, the necessity to simplify our ratios here has been in our last chapter, chapter 10. Okay, but it's going to come back to us right here in chapter 7. All right. Now, okay, warning though. Okay, before balancing, you must you must write all formulas as they are. This is the only time where you can adjust subscript. What I'm saying here is this. When it comes to doing that English to chemistry translation, that is the only time that you are able to write in your subscripts and make adjustments to your subscripts. Once you have written a formula, you are no longer able to adjust the subscript for a formula. Okay? So as soon as you have Mg, right? Like you've translated from the words magnesium chloride to the language of chemistry here, MgCl2. As soon as you have done that translation from magnesium chloride to MgCl2, and you've got your subscripts of 1, which are invisible, and our 2 for chlorine, you can no longer adjust these subscripts, okay? That is the only time you can adjust subscripts. That is what I'm referring to here. Once you have done that, okay, you have to go from there by only changing coefficients from whether you want to put a 1 here, which again is going to be invisible because we don't ever write the number 1, whether you want to make this a 2 or a 3 or a 4, right? You can change this coefficient to whatever you want to fit your needs, but you cannot change this invisible 1 to be anything other than a 1 and this 2 here to be anything other than a 2 for chlorine. Okay, you can only change your coefficients. Never change subscripts once you have written the formula. That's key, absolutely paramount. Okay. So again, before I move on from this slide to the last main concept for chapter 7 here, again, we're going to spend a lot of class time. So the next time I see you after you watch this video, pretty much all of our class time is going to be dedicated to writing formulas and essentially balancing these chemical equations, balancing these chemical reactions here, right? It's a very important concept. Being able to do it now is going to help pay off in the future because we're not going to stop balancing equations today, right? Or even next class or with our next assessment, right? It's something you're going to do later down in the school year between now and June, right? So you have people know how to do it at its most basic form now to be able to help do it later on. Okay. Now we're going to move on to our very, very last concept of this chapter already. Again, I told you chapter 7 is a quick one, okay? But the last one here are on types of chemical reactions, right? Types of chemical reactions. It's a pretty basic one. There are 4 main types of chemical reactions here. There are synthesis. 2 or more substances react to produce a single product. Also sometimes called a direct combination or a combination reaction. And it has a general form. Now, all of these chemical equation types, these chemical reaction types we're going to talk about, again, these 4 we're going to discuss today, they all have a general form. And when I say general form, I mean they just have A and B's and C's and D's as like placeholders for chemical formulas, right? So you can imagine that this A here could possibly be any of our chemical, or rather any of our elements, atomic symbols from the periodic table, right? This B would be then a different other elements symbol from the periodic table. In synthesis, guys, are when you've got 2 or more smaller pieces reacting together to form one larger piece, right? So this small piece in A is combining with this other smaller piece in B, forming a larger piece, AB, right? So you're taking a synthesis, right? You're synthesizing or sort of melding together 2 small pieces to create one larger piece here called synthesis, okay? Now, I also add in for all 4 of these chemical reaction types what to look for, because your main goal here, guys, is to be able to look at a chemical equation or a chemical reaction and to look at that reaction, look at the way it's set up, looking at your products and your reactants, and then make the determination what type of chemical reaction it is. If you are looking at a chemical reaction or chemical equation and you see 2 or more reactants forming only one product, that is what you should be looking for to help you find synthesis reactions, okay? So again, look at this here, general form. General form has got A plus B. That's 2 reactants reacting together to form only one product. So to look for, what to look for a synthesis reaction, 2 or more reactants forming one bigger product, okay? And this is a good example of that, right? The formation of sodium chloride, right? The table salt that you guys all know and love. Now, it basically takes solid sodium metal, right? 2 moles of it, right? That word moles, we're going to get to that next chapter. 2 moles of it, 2 whole moles of it right here, of 2 particles we'll call for right now. 2 particles of sodium are combining with chlorine gas, Cl2, which is that diatomic chlorine gas, to form 2 molecules of NaCl, right? 2 compounds of NaCl here, okay? So you're taking 2 smaller pieces to form one larger piece in this example here with synthesis. Now, what happens if you go in the opposite direction? Okay, that's what's known as a decomposition. And that idea of decomposition should kind of not be entirely a surprise to you guys, right? So that word decomposition kind of comes from some other sources that we've learned in science, right? Decomposition for a lot of us means the breaking down of something, right? And that doesn't really change here in the realm of chemistry. Decomposition is when a single compound breaks down into two or more simpler elements or compounds. And now we've got a general form here that looks pretty darn similar, which is basically the exact opposite of synthesis. Right? Synthesis had A plus B equals AB, but now decomposition has this one single larger piece as the reactant, right, as our main ingredient, and breaking down into two or more, in this case just two, smaller pieces, A and B. And what to look for would essentially be the exact opposite of synthesis once again, right? So decomposition and synthesis are complete opposites of each other, which is very, very convenient for us, okay? So what to look for whenever you're looking at chemical equations and you want to try to define one as decomposition, look for on the left-hand side of the arrow, one reactant, one big reactant, and on the right-hand side of the arrow as products, two or more products. And an example of that would be the breaking down of water, H2O, into its two elemental components, H2, which is hydrogen gas, and O2, which is oxygen gas. So we've got this one single larger piece here in H2O, which is a larger compound, breaking down our H2O into two smaller pieces, H2 and O2, right here. Okay, and that's a decomposition reaction. Now these next two aren't really opposites of each other, but they kind of work in tandem with each other. And this first one here, of the third in total here, is called a single replacement. Now a single replacement in its most basic form in terms of its definition are when the atoms of one element replace the atoms of another element in a compound. Okay, sometimes these are also referred to as redox reactions, and we will actually spend an entire chapter talking about these redox single replacement reactions, right? An entire chapter. It's actually the second to last chapter we'll do this school year, so it won't be until probably about May when we touch on this again, okay? But the generalized form here is this. You've got some element A and some compound BC. What happens here, guys, is this element A essentially comes in and reacts with the compound here, and what it ends up doing is it actually boots out the B from the compound BC. And basically the single replacement occurs here where there's only a single replacement of an element in the compound. So what happens is the A comes in, boots the B out, and the BOO leaves the compound and becomes the single element by itself. And that was exactly what happens over here. So now we have A combined with C, which has then booted B out to be by itself over here. Okay, and that is a single replacement reaction here. An example of that, or rather what to look for, is whenever you've got on the left-hand side as a reactant, one element and one compound reacting together to form another one element and one compound as products, but those elements and compounds on the product side are entirely different. So the element A over here, it has to be different than the element B over here as a product. Just like the compound BC on the left as a reactant needs to be entirely different than the product AC compound on the right. Okay, so everything on the left and everything on the right needs to be different, but it's still one element, one compound, and one element, one compound. Okay, that is a single replacement reaction. Now, the last one we talk about here, and actually before I get to that, this is a good example of a single replacement reaction here. It's whenever you've got this HCl molecule here, right, two compounds of it, HCl, reacting with the metal magnesium. And what happens is the magnesium comes into the formula here, right? This magnesium atom will essentially come in, react with the HCl, and it will actually boot out these two hydrogen atoms here. So these two hydrogen atoms will essentially get booted out to be by themselves. So that's why when we look on the right-hand side as products now, we have this magnesium bonding with the Cl here to create MgCl2, magnesium chloride. And now we've got these H2 atoms by themselves because, well, this H and this H got booted out to now create H2 as an element on the right-hand side. And now I want to quickly switch gears to our double replacement reaction here, guys. Take a quick second if you need to pause the video because it's going to end in a second here to get these notes, but I'll see you next class.